Manias. Talk about several modes in manifolds. The scope of this research is to explore the origin of the increasing accuracy provided by multi-scale and complex chemical kinetics mechanisms, in which fast reactions are in equilibrium and slow reactions drive the system. Firstly, I will make a short reference on the methane chemical kinetics mechanism. Then I will present you the theoretical background of my work, which includes stiff dynamical systems, the singular perturbation analysis, and the CSP algorithm. I will finish with presenting the diagnostics and the conclusions that were derived. Listed on this table are various chemical kinetics mechanisms accounting for methane oxidation that were developed over the last decades. Starting from simpler to more complex structures, the increasing size of these mechanisms increased the accuracy of which they reproduce the experimental data, but also they increase their complexity. The homogeneous adiabatic azochoric stoichiometric definition of methane air mixture is investigated here. I will make a comparison of two mechanisms. The first is the GRI mechanism that was introduced in 2000, and it's a very popular one about oxidation of methane. And the other one, that it will be referenced as the Galway mechanism, was introduced in 2015, and it is more regular. Now, even though these two chemical kinetics mechanisms are supposed to describe the same chemical phenomena, the parameters of their most significant reactions differ, and in some cases significantly. Here, there is the comparison of the reactions. In blue, there are reactions that their parameters differ moderately, while in red are reactions that their parameters differ significantly. The ignition delay time with respect with pressure is listed as figured. As you can see, the ignition delay time actually is the time where the ignition occurs. You can see that the Galway mechanism produces faster ignition delays. For both mechanisms, it is shown that they have the same trends. This similarity also extends to the species mass fraction profiles. Now, if we with the dashed line is the GRI mechanism, and with the solid line is the other mechanism, the Galway. If we see here, sorry for the many colors, some parts of the evolution of the species mass fractions are characterized by rapid variations, which are the red ones here, and the other ones, the variations in the other, the second part and the fourth part, are smooth. This indicates that a large time scale spectrum characterizes the dynamics of this system. Generally, this makes the system of such problems stiff. Generally speaking, stiffness is a feature that characterizes many physical phenomena, which are governed by time scales, by time scales that span into a large range. The major characteristics of such systems are that they have a large number of time scales. The fastest, some of them are much faster than the other and are of dissipative nature, which means that the components of the system that produces them tend to drive the system into equilibrium. Also, the solution is directed towards an n-m dimensional surface, which is the slowly varied manifold, or the SIM, where its evolution is characterized by the rest of the slow time scales. The classical approach of analyzing such systems is the singular perturbation analysis. However, this methodology is hindered in large and complex systems by difficulties that are related mostly when you try to set the system into a non-dimensional form, or when you want to decompose the variables into fast and slow. The geometric singular perturbation approach managed to overcome these difficulties by identifying the dynamical structures in the phase space, such as the manifold, and by exploiting their characteristics, like the decomposition of the tangent space into fast and slow subspaces. For example, consider a three-dimensional system, the trajectories of which in the phase space are attracted rapidly to a surface, along which they evolve slowly. Now, the geometric singular perturbation approach does not provide the tools to construct, to identify which this surface is, or what is the slow model that governs the flow on it. These tools are provided by the computational singular perturbation methodology, algorithm, or the CSP. More specifically, the CSP provides the basis vectors that span the fast and slow subspaces of the tangent space. This tangent space is introduced by a new non-orthocanonical basis vector, coordinate system. In this three-dimensional example, it is constructed in such a way where two of the three vectors are tangent to the surface, and the third is parallel to the directions where the fast time scale is act. This way, the vector field can be decomposed into fast and the slow component, where the fast component has negligible value on the seam. Now, as the solution moves along the manifold, these basis vectors rotate the field. CSP generally can be applied to any system despite the complexity or the size of the system, and can provide the basis vectors that span the slow and fast subdomains. By knowing the basis vectors, one can construct the manifold, and after the slow system that governs the flow on it. Now, the availability of the manifold and of the slow system lead us to the construction of low-dimensional and non-stiff models. In our case, the mathematical model that describes the adiabatic isochoric homogeneous ignition consists of the species and temperature equations, where y is the vector of the species mass fractions and the temperature. Now, if you want to construct a reduced model, the first step is to cast these two equations into a generalized form, and of the dimension n plus 1. Then you can decompose the vector field of this generalized system into the basis vectors by using the basis vectors of the CSP that span the fast and the slow subspace, where A are the column basis vectors and F are their related amplitudes along the directions of these vectors. The amplitudes are computed with the use of the basis dual vectors B. Now, when we are on the seam, the fast components of the system are exponentially small. Why? And that way, the vector field is simplified to only the slow components of the system. These two relations are the reduced model. The first one is an n-dimensional system of algebraic equations that define the manifold, and the other ones are an n plus 1 dimensional system of ordinary differential equations that governs the slow evolution of the process on the manifold. They're free of the fast time scales, and its dynamics is characterized by the fast of the slow time scales. Now, an interesting situation arises when some of the slow modes are of explosive character. Such modes tend to drive the system away from equilibrium and are directly responsible for the ignition process. Several reactions might contribute positively or negatively to the generation of these modes. And in order to analyze an explosive mode, the construction of a proper reduced model is of paramount importance. If you want to analyze the modes of a system, and in our case the explosive mode, we can use tools that that come from the CSP algorithm. Now, if we consider the Jacobian of the system, and if we decompose the eigenvalues by using the right and the left eigenvectors into a series of 2k terms, each one of the terms represent the contribution of a reaction to the eigenvalue and to its corresponding time scale. The relative contribution of a reaction to the eigenvalue can be measured by the time scale participation index. This is a tool of the CSP formulation. This is what we're going to use. Here are the explosive time scales that develop during the ignition, for both mechanisms. With the dashed line is the GRI mechanism, and with the black line, the solid line is the Galway mechanism. As you can see, two explosive time scales develop during the process. Now, this picture is not actually correct because I only display the fast explosive, the explosive time scales. I should also depict the dissipative explosive, the dissipative time scales. You would see a gap between some of the dissipative and this one, these two. This means that this is the fast explosive time scale, and is the fastest of the slow ones after the gap of time scales. If you also can see, in the Galway mechanism, the time scales, the fast time scale is faster than the one in the GRI mechanism. Now, the fast time scale, because it is much faster than the slow explosive time scale, it is the one that characterizes the dynamics of the system. Here is a trend in the previous picture. But we see that the Galway produces faster ignition delays because the fast explosive time scale is much faster than the other mechanism. In order to have a more precise view of the dynamics of the system, I will present you diagnostics that were taken in 5 indicative points. The first point represents the initiation of the process, while the last one indicates the point in time where the fast explosive time scale reaches its minimum value. Listed on this table are, for both mechanisms, are the reactions that contribute the most to the explosive time scale. With blue are depicted reactions that are present in both mechanisms. In red are reactions that only appear in the GRI mechanism, and red are reactions that only appear in the Galway mechanism. As you can see, the dominant chemistry for the most of the process, is different between these two mechanisms. For example, for the GRI mechanism, the major contributor to the fast explosive time scale is reaction 145 forward, which appears only in the GRI mechanism, and while in the Galway mechanism, reaction 19F is the major contributor to the fast explosive time scale. Both reactions support the explosive character of this time scale. You can see that this reaction actually exists also in the GRI, but it is only contributes in the Galway mechanism. Now, the first reaction is a chain branching reaction, carbon related, and the second is a chain branching hydrogen related reaction. In the last part of the process, even though some small differences in the dominant chemistry appear, the dominant chemistry is actually the same and hydrogen related. Now, in summary, the GRI mechanism, the reactions that are related mostly to the fast explosive time scale in the GRI mechanism are of carbon related chemistry, while in the Galway mechanism, the reactions that are major contributors to the fast explosive time scale are hydrogen chemistry related. Now, in conclusions, we used two different mechanisms that are supposed to describe the same experimental data. And even though they have similar trends, the dynamics of the process follows different paths. The CSP algorithm can manage these kind of systems, these problems, because it's an algorithmic method and the size or complexity does not matter. This way, the accuracy of a mechanism can be assessed on the basis of the physical diagnostics without the need of an experiment. This will take for your
questions, please. No?
Thank you.